The warm-up today is in My Open Math, so please make sure that you are putting your answers there. But let's go ahead and talk about this. I'll work this one out, and then we are taking notes today. The notes will be over forces and kinematics. I told you we're going to add something new, and it's really not something new, it's something old, because your kinematic equations are what we used in that second unit of the year. So we're going to bring back these guys that are on my board, and you'll see it again later on when we get to it in the notes. But you are going to want paper out for the notes today so that you can copy down some practice problems. You do have an assignment for homework, 401.3 Forces and Kinematics problem set. That is in My Open Math. It will be due tonight. And then the unit summary is also there in Schoology if you are looking for extra practice. Or if you want to use it for the bonus points or whatever, it's the back to normal, the same ones type that we've been using all year. But let me go ahead and bring up my document camera so that I can work out the problem that you see on my screen right now. So we're going to go over the warm-up, and then, like I said, then we will go ahead and get into today's notes. So I redrew the warm-up question on my paper so that I could work it out here. But it asked about a 25 Newton force being applied to a 5 kilogram block or box, I forget what it said, to accelerate it across a surface, a frictionless surface. And it asked us to find the acceleration of this object, and then the follow-up question was how would friction affect that? First things first, I want to point something out, because in all of our practice problems thus far, I think there was one similar to this, and may have even had the same picture in your My Open Math problem set the other day. But in most of our examples, the angles that you have been given have been measured from the horizontal. This one is measured from the vertical. You can see it in the picture, but they give you a vertical axis and they measure the angle from there. It's fine, you treat it the same way, but just be careful and pay attention to where that angle is so that you can appropriately calculate the components, okay, so that you have it drawn correctly. Ultimately, guys, we're trying to figure out the acceleration of this object, and this object is going to accelerate across the surface. So the acceleration of the object is going to be in the x direction, horizontally. Vertically, I'm not going to have any acceleration. Okay, so I don't really care about the vertical component of this. Don't care. It's not going to affect my horizontal acceleration. The only reason I would care about this is if I needed it in order to figure out my normal force, in order to figure out my frictional force, but I don't have any friction. So I don't actually need to calculate the vertical component of this. All I need is how much of this force is horizontal, because some of it is going this way, and that's what I need to find. Okay, I'm not going to do all the other steps if I don't need them. So we're going to solve for the x component of this 25 Newton force. And if you look at the triangle that I have formed, this component is opposite my angle. And I have the hypotenuse. And so if I have the hypotenuse and I'm trying to solve for the one that is opposite my angle, I'm going to be using sine. It's the SO and SOHCAHTOA. The sine of my angle will be equal to the opposite side, that's this one, I'll call it x, over hypotenuse. Okay, so let's go ahead and do that. So the sine of our angle, which is 60 degrees in this question, is equal to opposite over hypotenuse. Again, the SO and SOHCAHTOA. Opposite my angle is my x component of my force, and then my hypotenuse is this one, 25. Okay, again, I'm ultimately trying to isolate this, the x component, so I need to get the 25 out of here. We're going to multiply both sides by 25. Okay, that has now isolated my variable, and now this is what goes in my calculator, 25 times sine 60 degrees. Again, when you type this in, you need to make sure that you are in degree mode in your calculator. Okay, but 25 times sine 60 gives me 21.65 newtons as the x component of my force. That's not your answer because it didn't ask for the x component. It asks for the acceleration. I need this number in order to get the acceleration. So we're not finished yet, but we do have the first step done. Okay, so the x component of my force is 21.65. If I want to add another digit, I can put a 1 here because it was 6506 newtons. Okay, and so this is the force responsible for causing this to accelerate. It's also the net force. It's the only force in the x direction. All my vertical forces are going to balance. It said there's no friction. So this is my net force. It's the only force that I have acting on this object in the x direction. And so that force will be what is responsible for my acceleration. So I'm going to go back to this equation, F net equals m times a. Again, vertically I don't have a net force. It's 0 because vertically everything's going to cancel. This box is accelerating across the surface, not up and down. So again, the only thing that makes up my net force is going to be this one force. If I had friction, I would need to include it, but I don't. And so I'm going to say F net is 21.651, and it's equal to mass times acceleration. The mass is 5 times a. Okay, so if I want to solve for a, we're going to divide both sides by 5. And so that's what goes in the calculator. My answer divided by 5, and I get 4.33 meters per second squared. So that's the first answer, 4.33 meters per second squared. Does anybody have a question about number 1 in the warm-up? Number 2 in the warm-up says, how would friction affect the acceleration if this surface had friction? Okay, would this number be the same? No. Would I have more or less? Less. Because if I had friction, I would have had not just this force, I would also have had some amount of force going that way. That would have made my net force smaller than this because I would have had to subtract out the friction. And so then whenever I looked at this calculation down here, that smaller number would have resulted in a smaller acceleration. I'd have a smaller net force and therefore a smaller acceleration if friction were present. All right, guys, please make sure that you have your answers to the warm-up put in on My Open Math. And then, like I said, we're going to get into some notes. All right, so today we're going to start with some slides that should look super familiar to you because I borrowed them from last unit. And I am going to add some new stuff on, but I wanted to go over, like I said, just in the notes, some of the stuff we've already talked about and then before I add on the new stuff. So this one says a 2 kilogram box accelerates 12 meters per second squared to the right. What is the net force acting on the box? Okay, so there are 2 ways that you can find net force. You can find net force if all of the forces are labeled on your free body diagram simply by getting the sum of your forces in the x direction, the sum of your forces in the y direction. Okay, I don't have that here. I don't have a value where S is, so I don't know what that force is, so I cannot solve it in that way. The other way we can find net force is by using the equation F net equals m times a, which means we need mass and we need acceleration, and I do have both of those. They're in the question. So the net force here would be the mass, which is 2, times the acceleration, which is 12 meters per second to the right, or positive 12, which gives me a net force of 24 newtons to the right. Okay, pretty straightforward there. I think everybody's probably okay with that one. However, some of you yesterday were asking me how to find something like this. Okay, some of you yesterday still weren't sure how to find an unknown force like the one that's on my screen, unknown force S. I'm going to give you like 25 seconds to talk to your neighbor and see if you can figure out what S would be in this scenario. So turn and talk to them. Hopefully you're writing this stuff down as well. See if you can figure it out, and then we'll talk about it. Okay, so when I said some of you were having trouble with this yesterday, there was a question in your MyOpen Math assignment, and it said, it had you find net force just like we just did, but then it said something about somebody kicking a soccer ball. I think it was a soccer ball. Kicking a soccer ball, and it said, what's the force of friction if they kick it with this much force? And I had more than one person say, how do I find force of friction if I don't have the coefficient of friction? The same way you find force S here. Okay, if you know the net force and you know one of these, and there's only two forces and you know one of the two, yeah, you can find the third one. Okay, you can solve for that third force because net force is equal to the sum of the forces. You don't need a coefficient of friction, even if this were asking for friction. It's not specifically, but you can still find it in the exact same way that you should have done that one, and hopefully you figured it out yesterday as well. But F net in the x direction is the sum of my horizontal forces. Forces to the right plus forces to the left. Keeping in mind forces are vectors. So that one that's going to the left, you're not going to put 3, you're going to put -3. Okay, so 24 equals S plus -3. If I want to solve for S now, I'm going to be adding 3 to both sides, and I'm going to get 27 newtons. And some of you yesterday were showing me answers that said 21. Okay, that obviously you're forgetting about the sign here, or you're somehow doing the math wrong. I don't know. Okay, but make sure that your answer makes sense. If you have a net force of 24 newtons, that means that this force, S, is 24 newtons larger than this force. That's what it means. That's how you get that as your net force, because it's 24 newtons larger. 3 of it's canceled out. You still got 24 left, which means it had to have been 27. Okay, so you can go through it logically, you can go through it mathematically. I don't care how you get there, but you need to get the right answer. If you're missing that, that's going to mess you up later on if you're having to use it for another calculation or something. Does anybody have a question about anything on my screen? Again, this was in the last unit, so this screen should look familiar. So was this, by the way. Okay, it says, if the box moves to the left, will it get faster, slower, or have a constant speed? Take a look at my screen. If this box moves to the left, and I have to tell you that because you don't know which way it's going if I don't tell you that. If it moves to the left, what's it doing? It's accelerating, but more specifically, slowing down. Yeah, it's getting slower. Okay, so if it moves to the left, it is slowing down because the net force is to the right, which means the acceleration is to the right. If your acceleration and your velocity are opposite in direction, meaning you're moving in the positive direction but your acceleration is negative, or you're moving in the negative direction but your acceleration is positive. If you have opposite signs for your acceleration and velocity, you will slow down. The opposite's also true. If the signs are the same, negative velocity, negative acceleration, or positive velocity, positive acceleration, then you will speed up. Okay, you need to remember this stuff from Unit 2. Okay, so this would obviously slow down. What would that look like on a graph? Again, just to really quickly review, if we were moving to the left or backwards, we'd be down here. As we slow down, we get closer and closer and closer to 0. And so your graph would look something like that. Okay, here is the part that's new. Okay, the rest of the slide you've seen before. This you haven't. Okay, it says, if the box is initially moving 16 meters per second to the left, how long will it take the box to stop? You guys told me just a second ago, if it's moving to the left, it's slowing down, which means it will eventually stop. Okay, if those forces continue to be applied to it, it will stop. And that's what this wants to know. How long will that take? How many seconds will that take? And how far will it go before it stops? Those are the two questions on my screen. We're going to solve the first one first, but in order for us to solve it, if we look at our equations that I have for this unit on forces, there's no time in any of my equations. F net equals ma, there's no time. Ff equals mu times Fn, there's no time. Fg, there's no time. If you are asked a question where you're being asked to solve for time, or a final velocity, or a displacement, you're going to have to go back to these equations that you learned earlier in the year. Your kinematic equations, because they also have acceleration in them. We can use forces to find acceleration with F net equals ma, but we can also find acceleration here, or use the acceleration we found in these equations to solve for something else, okay, which is what we're going to be doing. So again, it's not really anything new. I'm bringing back in old stuff, and now we're going to combine the two units together. So if the box is initially moving 16 meters per second left, how long will it take the box to stop? Guys, now that we have these four equations in addition to the other ones, it's super important that you label everything so you can figure out what the heck to do with it. Okay, so let's label everything we know. We know the acceleration is positive 12. We know the initial velocity is negative 16. Again, we found these on the previous screen. We got the acceleration. Here is negative 16 because it's 16 meters per second to the left in the question. We know the final velocity will be 0 because it's asking how long it takes the box to stop. Okay, so we want a final velocity of 0. And we're trying to find how long, which means we're looking for time. If you label those things, you have A, you have VI, you have VF, you do have F net, that's not helpful here, and you're looking for time. Okay, and so look at your equations. They're the same ones as before. They're lettered A, B, C, and D. Which equation would allow me to solve for time with the information that I have? A. You're going to use that equation right there. VF equals VI plus A times T. And if I use that equation and substitute, and I get this. 0 equals negative 16 plus 12 times T. And guys, it is important that you get your signs right. Okay, otherwise you're going to get, in this case, you'd get a negative time, which would be like, something's wrong. Okay, it's important that you get your signs right. Sometimes it gives you the wrong answer as well, not just the wrong sign. So make sure that your signs are right. I did see somebody the other day doing a problem kind of like this, and they tried to add these numbers together, and they said negative 4t, and you cannot do that. Okay, please don't add those. Those are not like terms. If you're trying to isolate that variable, that t, and get it by itself, you need to move the negative 16 to the other side. Right now it's being added, but it's a negative number. You're really subtracting. So you're going to add 16 to both sides to cancel it out. Okay, so 16 equals 12t. To isolate t, divide both sides by 12. 16 divided by 12 gives me 1.3 repeating. 1.33333 seconds. Okay, so that's the answer to the first one. How long will it take? 1.33 seconds. The second question up here was how far will it travel before it stops? So it's traveling to the left. It is slowing down. It takes it 1.33 seconds. How far does it go during that time? We're looking for delta x. Okay, now at this point we know A, VI, VF, and T. So we can actually find delta x with either equation B, C, or D. Again, I would recommend C or D because they're easier because they're already set up to equal delta x. In this example, I used equation D, but if you used C, there's nothing wrong with that, or even B. Delta x equals VI plus VF over 2, or 1/2 VI plus VF times T. Okay, so that's 1/2 negative 16 plus 0 times 1.33. Half of negative 16 is negative 8. Negative 8 times 1.33 is negative 10.67 meters. Okay, that is your displacement. And it's a negative number because, remember, you're moving to the left. It said so in the question. So you're going to end up with a displacement that is also to the left. 10.67 meters to the left. Does anybody have a question? Yes, sir.
I got 10.64.
I don't know. I did it the other day. Yeah, my last digit might be wrong. I don't know. I may have typed it wrong. No, it's right. It's if you don't round it. Yeah, I use the unrounded 1.3 repeating, and you get that. Okay. So we have combined kinematics in with our forces. Let's do it with an elevator problem. Okay, so it says, Simon, with a mass of 85 kilograms, stands on a bathroom scale in an elevator car as shown. While the elevator moves downward, Simon steps on the scale and notices that the scale reads 1,003 newtons. Let's start with number 1. Draw a free body diagram showing all the forces. Okay, if we're drawing a free body diagram, there's only 2 forces we need to show in this elevator. Fg, force of gravity acting on Simon, and Fn. Now, without me doing any math, I don't know if these are the same length or not. I do know that if we're in an elevator that it's possible for these to be equal to each other or for Fn to be longer or shorter than Fg, and I don't know which it is until I do the math, so I'm just drawing them without caring about the lengths right now. Okay, but those are my forces. Step 2 is calculate Simon's acceleration. But before we can find acceleration, we have to first find net force. Okay, so I've got 2 forces up here, Fn and Fg, and the question actually gives me one of them because it says the scale reads 1,003 newtons. As a reminder, a scale reads normal force. So that 1,003 newtons is the normal force. And I can find my net force as the sum of my forces, Fn plus Fg. Fn is positive, Fg, though, is going to be negative. Okay, Fg is m times g, which is 85 times negative 9.8. Okay, so I have my Fn 1003 plus Fg, 85 times negative 9.8, which happens to be negative 833. And I get a net force of positive 170 newtons. Okay, so although when I first drew my diagram, I didn't know whether to draw Fn longer or shorter, now I know. Because I have a positive net force, I need to make sure my Fn is longer. So I just made it longer. Okay, now they're at least somewhat to scale. Okay, so Fn is longer than Fg in this problem. Because Fn is 1003 and Fg is 833. All right, so we found step 2, we haven't found step 2. We found Fnet. We need to use it to find the acceleration. And again, if I'm trying to find acceleration and I've got net force and mass, I just use Fnet equals ma. 170 equals 85, that's the mass in the question, times a. Divide both sides by 85. 170 divided by 85 is positive 2. Positive 2 meters per second squared. Again, I know that it's positive because I know my acceleration will be in the same direction as my net force, and my net force was positive 170. Does anybody have a question so far? Guys, these problems work exactly the same way as the ones moving horizontally. Whenever you're doing the net force and all of that, it's the same stuff. Okay, I know it seems a little trickier, okay, but ultimately it's the same process. All right. The next step, number 3, is he speeding up, slowing down, or moving with constant speed? Okay, I do not want you to look at that previous answer and say, oh, positive 2 meters per second squared, he's speeding up. Because that's not what an acceleration of positive 2 means. That does not mean you're speeding up. It could, but you can't just look at that. To answer the question whether he's speeding up, slowing down, or moving at a constant speed, you need to know not just the direction of the acceleration, but also the direction of his motion, the velocity. The question gives us that. It says he's moving downward. If he's moving downward, but his acceleration is upward, is he going to slow down, speed up, or stay at constant speed? He's going to slow down. Again, this is probably the 4th time I'm saying this, so if you haven't written it down yet, you probably should. If your velocity and acceleration are in opposite directions, you will slow down. If they're in the same direction, if he was downward and his acceleration was also negative, he would speed up. Okay, so again, you can't just say, oh, positive 2, he's speeding up. Not in this case. In this case, he's moving down. Let's say his velocity starts at 6, okay, negative 6, and then it's negative 4, and then it's negative 2, and then it's 0. Okay, the change each second with those numbers is positive 2, just like this example. Okay, but he's moving down to a stop. He's slowing down. Okay, so positive acceleration while you're moving in the negative direction causes you to slow down. All right, the last question up here. If the elevator's initial speed was 3 meters per second when Simon stepped on the scale, how fast is it moving after 1.3 seconds? We're going to answer that one now. Give me some space. I'm going to go ahead and copy my acceleration down because we're going to need it. Okay, how fast is it moving after 1.3 seconds? If I'm trying to solve for a velocity, a final velocity, I need to come back to these equations over here. So let's label what we know. We know the acceleration. The question gives us an initial speed. It says the speed is 3 meters per second. Well, my velocity needs a direction. Speed is scalar, but my velocity is 3 meters per second downward, because the question says he's going downward. So my velocity is -3 initially. My acceleration is +2. The time in the question is 1.3, and I'm trying to figure out how fast he's going at the end of that time. So we're solving for VF. Okay, with these 4 variables on my screen, if I take a look at my equations, the one I'm going to use is equation A. VF equals VI plus A times T. Substituting in, I get this. And this is why your sign matters. If you don't put -3, you're going to get a completely wrong answer. -3 equals 2 times 1.3. 2 times 1.3 is 2.6. -3 plus 2.6 is -0.4 meters per second. So his final velocity, he's still moving down. He's almost stopped, but he hasn't quite stopped yet. Okay, his velocity is still -0.4 meters per second. All right. So again, you should be able to use these kinematic equations in conjunction with the force stuff that we've been doing. Let's look at one last example. This time we're going to bring in an angle. Okay, it says a man's 50-kilogram boat was stuck on shore when the tide went out. He pushes his boat at a downward angle of 20 degrees with the ground to move the boat from rest. After 20 meters, he reaches the water with the boat moving 5 meters per second. Okay, so I've got a picture here so you get an idea of what this scenario would look like, but let's look at what questions we're going to answer. What is the acceleration of the boat? What is the net force on the boat? Assuming no friction, what force does the man apply when pushing the boat? And what is the normal force acting on the boat? Okay, so we've got 4 different things that we're going to answer here. So let's start with number 1. What is the acceleration of the boat? Again, I can find acceleration in a couple of different ways, but because I have so many equations to choose from now, let's start by labeling the information we have. We have a mass of 50 kilograms. We know that he pushes the boat with some amount of force at an angle, but we don't know what that force is. So that angle is actually not really useful to me right now, so I'm not going to write it down unless I actually have a force to go with it. But I do know his initial velocity was 0 because the boat was stuck. He moved it from rest. I know that the displacement of the boat is 20 meters. I know that the boat's final velocity is 5 meters per second. All of those things are in the question. Okay, there's nothing in the question related to forces at all. And so if I'm trying to find acceleration, rather than starting with the forces, since I don't know them, we can instead start with our kinematic equations because I do know a bunch of stuff that would be useful here. I should be able to solve for acceleration when I know VI, delta x, and VF. Okay, but these are all the possible equations that you could use in this unit because these are all the equations that have acceleration in them. F net equals m times a. Can't use it. Don't know F net. VF equals VI plus a times t. Can't use it. Don't know t. Okay, the only one on my screen that I know all of the variables for and that I could use in one step is this third one. The other ones, I don't know the stuff in red. But this one, VF squared equals VI squared plus 2 times A times delta X, yes, I can use that. And so that's what we're going to do. We're going to substitute into that equation. VF squared is 5 squared equals VI squared, 0 squared plus 2 times A times 20. 5 squared is 25, 2 times 20 is 40. Okay, so we're going to get A by itself by dividing both sides by 40. 25 divided by 40 is positive 0.625 meters per second squared. Again, he's pushing this from rest, and he's going in the positive direction. So I know he's got to be speeding up in the positive direction, and I have a positive acceleration that makes sense. Okay, so I got my acceleration, but I didn't start with forces. I started with kinematics, and that's okay. Now that we have acceleration, we can use it to solve other stuff here or over there, because if we know acceleration, we can also learn some stuff about our forces, which is question 2. What is the net force on the boat? F net equals m times a. We know the acceleration, we know the mass, 50 times 0.625, we get a net force of positive 31.25 newtons. Or you can write it as 31.25 newtons to the right. Okay, so we have our net force. We used our acceleration, we got it from kinematics, then we used it over there. Third question, assuming no friction, what force does the man apply when pushing the boat? Okay, well, I know that the man is applying a diagonal force. Okay, it looks like that. It's described in the question as 20 degrees with the ground, okay, but he's applying the force like that. And I know that a portion of his force is vertical and a portion of it's horizontal. Anytime something's at an angle, pieces of it are going to be horizontal, pieces of it are going to be vertical. Which part of his force is responsible for the boat's acceleration? Just the horizontal piece. Okay, the vertical piece, not at all responsible for the acceleration. So that net force that I just found, it's not this red vector. This net force of 31.25 newtons to the right, well, guess what? It's to the right whenever we draw the triangle. That net force goes here. 31.25 newtons. It's not the hypotenuse. It's the x component because it's responsible for the acceleration. It's to the right. It's not at an angle. Only that part was used for the acceleration. So this time I know the angle and I know the adjacent side. I can use that to find the other two sides. Now ultimately I want to find FA, because that's this question, how much force does he apply when pushing the boat? That would be the diagonal one. But I am going to go ahead and find FA in the y direction as well, because the fourth question on my screen was about normal force, and that means I do need to know the vertical stuff too. Okay, so if I wanted to find the vertical component FAY, I would use tangent. Tangent of angle 20 degrees equals opposite over adjacent. That's TOA in SOHCAHTOA. But opposite over adjacent. And so if I multiply both sides by 31.25, I get 11.374 newtons. That's the y component. That's not my answer to this question, but I'm going to need it in a minute. The answer to this question, how much force does the man apply, is the hypotenuse. That's his applied force. I don't want the components for this question. I actually need the hypotenuse. Okay, and so let's go ahead and solve for FA. Okay, I'm going to use trig, although at this point, because you know the other two sides, you could also solve it with Pythagorean theorem. That would also work, okay, because you know the other two sides. But I did this. Okay, I used cosine because, again, I have the adjacent side and I'm looking for the hypotenuse. I already rearranged it. And so F sub A, my hypotenuse, is equal to 31.25 divided by cosine 20, which gives me an answer of 33.256 newtons. That is the force the man applies. Only 31.25 newtons of it is causes the acceleration. Okay, that's my net force. But that's the total force that he applied, is the hypotenuse, the diagonal one. Okay, so from here, there was one more question we had to solve. What is the normal force on the boat? You'll notice that I put these on a free body diagram. Okay, so I have the horizontal component of his force. I have the vertical component of his force. I don't care about the diagonal on my diagram. I don't want to see it. Okay, just put the components. Okay, but if I want to solve for normal force, I need to find FG because this boat is accelerating horizontally. Vertically, it's not accelerating at all. And so I know that Fn, which is the only force I have going up this time, is going to be equal to Fg plus that 11.374 newtons. Yesterday, most of our stuff was being pulled upward at an angle. This one's being pushed downward at an angle. So you'll notice that that component's on the downside now, but it's the same idea. My vertical forces still need to be balanced. I can find Fg, okay, using Fg equals m times g, and that'll help me figure out what Fn is because, again, I know that the vertical forces are balanced. Fg equals 50 times negative 9.8, which is 490. Technically, it's negative 490, but when I put it on here, I don't need to put the negative sign. So now I know the total downward force. Fn is going to be equal to the sum of those. All you have to do is add them together. Okay, you can also do it with the equation F net y. I know it's 0. I know they're balanced, and it's equal to forces up plus forces down. keeping in mind that they're vectors. So my downward ones are negative. Negative 490 plus negative 11.374 plus Fn will equal 0. But all that is doing is saying, hey, if you add the two bottom ones together, it gives you the top one. You didn't have to do that equation to get there. Okay, if you knew that net force was 0, you could have done this without writing out all the math. This is one of the few times I'll say that. But 490 plus 11.374 is 501.374 newtons. That is your normal force acting on the boat. Does anybody have a question about this one? So again, we're not adding anything new, we're adding something old. We're bringing back our kinematic equations, and that's what you're going to be working on in your assignment today. So if you would please make your way to My Open Math and open up 401.3 Force and Kinematics problem set. Work on what you can in class today. If you have questions as you're working, you guys do have 10 minutes or so, 15 minutes. Of course, it's an advisory day, so you'll have advisory too. But you have some time to work on it, ask questions if you get stuck. But it's due tonight by 11:59 p.m. So please work on it. If you have questions, let me know.